So here with chapter 8, we are now studying non-linear missing data. So we here's the setup. X, Y, random variable. Y is subject to missingness, and a response indicator function is a 1 or 0 if delta equal to 1, if Y is observed, and delta equal to 0 otherwise. Non-linear response means this case. So if this is holds equality, then it is missing a random, right? So it's just a not more challenging case of the not missing a random. Okay. So so then question is, what should we do? So suppose we have a model. So suppose we have a model. Now it depends on Y in addition to X. So then we are interested in, we may use this. So this is the observed likelihood, right? So you delta equal to 1, you observe X and Y. So you can just use the joint density. Delta equal to 0, you don't observe Y. So you integrate out over Y, right? So that is the all information. So this is basically what? This is the conditional property over delta equal to 0 given X and Y. And you just take the Y is now observed, so you want to take the integration over Y. So that then you have X information and the information that delta equal to 0. So that's
notation phi of delta given X and Y.
Huh?
What is this notation?
First one?
No, the first second one.
Okay.
So the phi delta. Yeah.
Okay. Sorry, it's a typo, right? Thank you. Oops. So this is actually okay. Yeah, thank you. So this is just a pi xy. This guy. So now we want to maximize this basically, right? We want to maximize this, but before we maximize this one, the first question we want to ask ourselves is whether the model is valid model to compute the MLE. So we need a model identification condition first. So here's remember this is the definition of the identifiability condition. So we have a model, and model has a parameter. So parameter is more like a coordinate system. So you just we change over theta, and so different value of theta determines a different distribution, right? Essentially. And now question is, what do you mean by this model is identifiable? Well, as a function of theta, this is should be 1-to-1. Okay, so that means two different parameter values should represent different, right? So different distribution. Okay. So identifiability is a concept closely related to ability to estimate the parameter of a model from the sample generated by the model. Okay. So first lemma, I think this is what we already discussed. So this is the odd function based on conditional distribution, while this is the conditional on X only. And then this is, so how you gonna, so this is the OXY FY given X property delta equal to 1 given X and Y, right? And then the Y denominator something like that. And then you basically have some simplification. So if you, So by this property, the product of the two is actually becomes a, so product of the two becomes a what property delta equal to 0 given x and y, right? So that basically means you are integrate. So then you this one is actually then the numerator becomes expectation of the, so numerator becomes this and denominator becomes this. Okay. So I don't know. So anyway, this is one result we're going to use later. So now the previous likelihood here, the likelihood function is here, right? This is the observed likelihood function. And now we want to express it slightly differently. So the first one, same mistake. So first one is this one, right? So first one is already what we wrote before. And now we want to rewrite it slightly differently. So basically, you can write it, you are writing, so y given x times g delta. So this is the density xy. Okay, so conditional density of the delta given x and y. So that is the joint. And now you can write it as a, you can now writing it as a delta and then g so what am I doing? Okay. This is what I'm trying to do, but this is not exactly correct. I think what, so okay, let's understand this way. So this is essentially joint density of delta n x y. I'm sorry, delta n y given x, right? And now the joint, okay. So right, so this is the joint density. If you write, so this is the density of delta given x and y. You have three random variables essentially, and so y given x, delta given x and y time will make delta and y given x, right? That part should be okay. And now what I'm trying to do is to, so how to write, so you have a different way of, so now let's write it. So joint is a conditional times marginal. So conditional, so let's write it, the conditional and marginal. Yeah. So this is another way. So this is, if you write it this way, you have a y and delta given x. So essentially same. So you can either write it this way, joint, or this. Okay. Huh?
The second expression value is x y given x delta.
So forget about x, okay? X is a both given. So that this is marginal of y, and this is condition of delta given y. So then product with a joint, right? Marginal y given, okay. Yeah, I mean, so okay, the left side is nothing but y and and delta given y. Okay. So, but you can write it as a y given delta and delta. Right? And then conditional both sides with conditional on x. Then this is it. Okay. Okay, now if you do that, so now we're gonna change it to the second expression. Okay. So we're gonna use this expression to write down the observed line. So delta equal to 1, you just write down so delta equal to 1, you write down this part times this part, right? So this part times this part. Okay. And now delta equal to 0, we need to take the integration over y. So if you take the integration over y, this one has nothing to do with the integration y. So this is just the integration of this guy only. So this integration disappeared. Is equal to 1. So then only this one remains, which is this one. Okay. Why we don't have a much attendance today?
Actually, they all go for the same on-site interview.
Huh?
They all go for the same on-site interview.
Some exam?
The interview.
Oh, interview. Okay. I see. Okay. Okay, no problem. They can attend the YouTube. So, okay. So basically, this guy, right? This guy. So this is one part for delta equal to 1. Delta equal to 0, we have only this part. Because your integration over y it becomes equal to 1. So you have this simplification. So once you write this way, huh? So pi theta is this. You're taking integration. So because this is the large delta given x. So how do you define delta given x? Use this. Okay, conditional property of delta given x. Okay. So once you write this way,
But you are saying that the integration of f of y given x is integrating out. So it is 1. Then you are saying that pi theta should be the integration of this 2.
maybe so okay. So delta equal to 1, for delta equal to 1, we should not integrate over y because we observe y, right? But delta equal to 0, we don't observe y, so we need to take the integration. So then the integration over y on this first part is equal to 1.
So in the second line,
Okay.
where you write pi theta xi comma pi to the power delta I. So there wouldn't that be pi theta xi yi as pi, because for delta I equals to 1, we are not doing integration. So the first
So this one is here. So this one delta equal to 1, this one is here.
So you are writing the opposite thing, that term is not the right term in both places, right?
So okay. Well, so we don't really have to write this guy and just do whole thing, right? So what I'm doing is for delta equal to 1, we need these two. So this is 1 and 2. Delta equal to 0, we don't need the first term because it will integrate out to 1. So then we only have a second term, which is this one.
But my point is here, pi theta is integration in terms of pi and f of y given x.
Okay.
My problem is here. So why we are defining as pi theta x pi?
Pi tilde x, y depends on phi.
Now, the integration of pi, yeah,
So why we have this equality?
yeah.
Oh, okay. So, okay, this is what? This is the definition of this one is delta equal to 1 given x and y, right? Which is the conditional expectation of delta given x and y. So that is the basic conditional expectation, the property of conditional expectation, right? So the conditional expectation. So conditional expectation of the, I think this is what we are doing here. So essentially we are doing something like this. Okay. So basically this is okay. So okay, so then huh? Delta given x and y. Okay. So that that actually create so now why we are doing this? Well, we wanna our goal is to whether we are investigating the identifiability, right? So idea is less. So the most of the information about phi is actually in the second one. So really it should be. So we can consider this one. So this one is actually logarithmic. I mean logarithmic function of the Bernoulli distribution of this probability, which is the conditional probability. So this is actually conditional expectation of the pi x and y, right? Phi given x. So and then the relationship between all these other functions. So we have two types of responsibility. One is the conditional on x and y. The other one is the conditional on x only, but it's a still function of phi. And so the one of the finding is that lemma is that so the identifiability of pi xy phi can be determined by the identifiability of this function. So conditional expectation of the as function.
But why we are not interested in the parameter theta, which is the response model parameter? So why we are not interested in identifiability of pi?
So we are no, we are interested in we may be interested in theta later, but for now we are focusing on estimate because this one characterizes. So this one really characterizes the response probability, and given the observed data, question is how complex we can build a model. So later we'll see that if you make the model more complex, then we cannot really identify the parameter. So because we have limited information, we'll see that. So here's an example. This is a very important example to understanding the concept of the model identification. So under the logistic regression model, suppose your logistic regression model. So suppose you have a response probability is a logistic regression model, and then the R function. So R is 1 minus, right? 1 minus pi divided by 1 minus pi. So that is actually the numerator. So R function is in this case is just the exponential function. Okay, and now the conditional expectation of this guy given x is just the conditional expectation on the exponential function of y. So then you use the MGF. So because in this case this is normal, so what is the expectation of the py given x? MGF, right? Property of the MGF. So this is actually mu t plus 1/2 t squared sigma squared, something like that, right? So that is the if you know if y is normal, then the conditional expectation. So if this conditional expectation is normal, then you have a closed form. And now the form, so mu corresponding, so t is actually p2 minus p2, and then tau, mu is tau x, and sigma is sigma squared, right? So you can actually write down. So you have a closed form result. To understand what's going on. Okay, so now to apply this lemma 2, we want to check whether this one as a function of phi is 1-to-1. So here the function parameter is a 3-dimensional, p0, p1, p2. Okay, so then is this completely determined by, so as a p1, p2, p0, p1, p2, 3 parameters. So is this completely determined by 3 parameters? When suppose this is tau is constant, suppose tau is 0, then see what happens. So if tau is 0, then you have an exponential of the minus p0 minus sigma p. So constant, so inside is exponential function, you have a linear function of x. Okay, then you cannot really identify 3 parameters with the 2 sophisticated statistics. Know what I mean? So here, so if tau x is constant or linear, then inside you have a basically linear function at most. But you have 3 unknowns, right? You have 3 unknowns, p0, p1, p2, 3 unknowns, and you have a basically linear function. Then different parameters give the same linear function, right? So then you cannot really identify. So that means your model, your conditional model, y given x, your f1, y given x should contain at least quadratic term. Okay, so if you contain quadratic function here, then now you have this is a quadratic function. Okay, then you have 3 parameter with 3 quadratic, right? So 1, x1, and x2, x squared. So that means you can actually completely identify, determine the parameter. So that means you need some sort of the complex model. So that means same story. If you have a okay, so suppose your model contains phi3 at xy. Okay, suppose you have a phi3 xy, then you are in trouble because you have a 4 unknown parameter with quadratic. Right? If you have a quadratic, then you have a 3 sophisticated statistic with 4 parameters. So that means you cannot really identify if you have a. So that means you really need some sort of a simple model, relatively simple model in the response mechanism in order to identify the parameters. This is kind of important.
So then, if there's the additional parameter which is 5, 3, xi, yi, then we need the outcome model which is yi given everything else to have tau xi to have like cubic parameters.
Yeah, so you need a more complex model, right? So if you make more parameters here, if you add more parameters, so if you make then you basically, because of missing data, you have less information. So originally, right? Originally, if you don't have any missing data, then you have enough information to compute all these parameters. But because this y is missing, right? Because y is missing, you are losing some information. So for example, if you have a if you have a say phi3 y3 y square, right? Then you don't observe y to estimate p2, and you don't observe y square to estimate p3, right? So you are actually giving more burden to the model, given that you have a limited information, right? So you have a given information. If you keep adding more complex models here, you are actually making problems more complicated than necessary, right? So that means you have to compromise. You have to compromise, and that means you either increase the complexity of the model in F1 to identify to make this one more extra terms, or you can simplify the model, right? Because it is really about how to how can you match your information with the unknown parameters in the response model and do some bias correction later.
So basically, you're saying that here, since y is missing here, so we will not complicate our model including the y. So instead, we're including the terms instead of the observed part, like the x. Right. So that's why you're complicating your model with some terms with x instead of y.
So yeah, I think so. Basically, we are kind of believe that the response mechanism depends on y, right? Because if we the really exists way is just that p2 equal to 0, right? If you put p2 equal to 0, then it's missing a random. Then you don't really have to worry about anything, right? But they may not be realistic, right? We sometimes we know that missing mechanism may depend on y. So we want to include that possibility into our framework, right? Estimation framework. So it's okay to include this P2y to our model. Then we should be very careful to make sure that we need to at least make it more quadratic term here, for example, to identify the model. Otherwise, if you just do linear, if you do have a linear, then you cannot really solve the problem because you don't have information.
So basically, having more complex pi I, that means it is more complex. So we have to get some idea from missing yi also. To get that, we need more complicated model for the response itself. Otherwise, to connect yi to xi.
Right. Well, in other words, we need a simple model.
Or
relatively simple model. Okay.
So x is complete here. So if we add some, just like 3x squared, that's one. In fact, I didn't know the model.
Huh?
If I add some term that is only related to x.
I see. That's a good question. So you mean if I have a p2x p3x squared, right? That's a good question. But still, end of the day, we really want this to be one to a function of phi.
And then also we need more complex.
Yeah, I mean, because adding more parameter is actually, it's like having more unknowns. So it's about information versus the information you have versus unknowns. So parameters are number of unknowns, and this sufficient statistic is the information that we have. Okay. So this is one of the results. So that means we need, so remember, so the motivation is that we need to sacrifice, so we need to simplify our model in order to, so one easiest way is that maybe the response mechanism depends on, we allow it depends on Y, but we don't have to include all the covariate, all the X variables. So we intentionally set this X2, okay, so that we have a simpler model. Okay, so reduced model. But this X2 is relevant, still important in predicting Y. Okay, so that is the assumption. Then under that conditions, the models are identified, parameters are identified.
How do you equal the equation to
Huh?
real given Y is equal to real given Y is so?
This one?
This one, how do you?
So that means it doesn't depend on X2. Okay, so this response mechanism may depend on Y, may depend on X1, but not depend on X2. So let's use the same example. Now let's consider X is X1 and X2. So then the response method. Now, if I use this assumption X2, right? So X2 is not included. So I intentionally exclude X2 here. Okay, exclude X2 here. Then see what happens. So in this case, the exponential function, the odd function, you have something like this. So then that means if tau x is a linear function of x2, so if this one is a linear, has a non-constant function of x2, then you can actually identify, because you have 3 unknown. So that means you need something other than 1 and x1, right? So then you need x2, then you can identify.
So is it necessary, like, if tau x is not a non-constant function of x2, but let's say tau x is x1 square, then also it is identical.
Yeah, right.
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 This is one of the possibilities.
One of the possible, right. But since we observe, right, since we observe x1, x2 throughout the sample, so then it makes sense to build x2 with the model, right? And so you include, the point is that you include x2 here, but exclude x2 here. Okay? That way you can basically, so remember, the main problem for estimating this one is that we don't observe Y in the sample, right? We don't observe Y for delta equal to 0. We cannot really use Y to estimate the parameter. So this x2, which is related to Y, can be used to somehow as a substitute, right? I mean, some kind of proxy for Y2, for Y. And because we can use x2 to estimate the parameter. So we'll cover the estimation later, but the main point is, main reason is that we don't really have information for P2. So we need something additional, right? So that is the basic idea. Okay. Yeah. So this kind of identifiability issue was regarded as a mystery for a while, but this is one of the contributions that we made to the literature. So basically the condition is this. So we identify some variable that there's independent y. I mean to delta given y. So that means x2 explains y, and delta is a function of y and x1. Okay, so that is x2 still related to delta through y. It's instrumental variable. Okay. Now let's move on to conditional likelihood approach. So now, so this is a different topic. Suppose we are interested in estimating zeta, and if phi is known, so this is some cases suppose we know this, okay, then see what you can do. So one way, in this case, we can remember that we write we have a expression, right? Also write this expression something like this before, and now the first one, the first component, which is this one, can be written as this because of the Bayes theorem, right? You have a Bayes theorem, so this is the property delta equal to 1, and you do something like this. Okay. So the conditional likelihood is essentially conditional on delta equal to 1. So the likelihood corresponding to conditional on delta equal to 1. That way we can use the only, so we want to use the delta equal to 1 cases only. Okay. Suppose I really want to use the delta equal to 1 cases. Then it's a CC analysis, right? So then if I naively use CC analysis, then it could be biased. But if I do this proper adjustment, then it's okay. So basically, this is the scope function derived from the conditional likelihood is this first one, right? So this one. Now let's derive the scope function. So how to compute? You take the log, right? You take the log, and then this is summation delta I equal to 1, and then log f yi given xi zeta plus constant minus something, so minus log of integration. Right? So that is basically the log likelihood. You have something, this one, and then this one is just constant, and then you have zeta here and zeta here. And now you want to take the differentiation with zeta. So if you take the differentiation zeta first term, this is just the scope function, right? And now the differentiation with respect to this term, second term, is basically becomes this. So why? Because you want to do So you want to do and then differentiation, right? Okay. So then how to compute? So denominator is just so denominator that doesn't really, do much. But the first one, if you do that, then this is a score times density, right? So partial derivative of the density is a score times the density. And then basically, so that is actually C, what? So then you have a score function times pi density respect to all this, right? So that is actually what? F y given x delta equal to 1 dy. Because the density with pi is the density with the y given x and delta equal to 1. So this density is this one. So we use that in this computation. Okay. So that leads to equation 4. So 2 ways, right? So if you use Fy given x and delta equal to 1, then this is just conditional expectation. Like this. But you can spell out using the basic formula that we used in deriving this equality, right? So if you use this one, then you can write it as something like this. Because same thing, right? You conditional, how to reflect conditional on delta equal to 1. You apply that's exactly what we did here, right? So how you interpret this? So changing from here, so you use the original density, but you now have a weight function, pi. So that is this one. So you just apply weight function, pi, and then compute the original. Use the original density, which is y given x. And then the second term, so that's interesting. So basically, if you ignore second term, right? Then you know that the expectation is not equal to 0. So we want to make the expectation of this, the whole function equal to 0. So that means we are doing kind of a bias on this. Okay. So the second term can be understood as a bias term. And so we subset the bias, then it becomes a unbiased estimate. Okay. And of course, if you notice that so since we write this way, right, this weight function, but if pi xy is a function of x, then we can actually cancel it. So that we have a MAR situation, right? So then in the MAR situation, then the bias correction term is equal to 0. Okay. So now, how to solve it exactly? So remember, so if you look at this carefully, you have a dependency of zeta in 3 places. Zeta here, zeta numerator, right? So original scope function, you have a zeta dependence. And then in the bias fraction term, you have a zeta dependence in S, and also when you compute the conditional expectation, you have a dependence on zeta. So that means you need to compute the partial differentiation using chain rule, right? One by one. So first one is just this one. Second one, you want to apply it to the numerator. So the numerator, okay. So numerator, you have 2 places in the numerator, right? So then you first one is in here, right? And then second one, what is the partial derivative in the second term? It's actually density, right? It's a density. So you apply the partial derivative to the density, then you have a scope function times density. So that actually gives this one. And then denominator is this. And then finally, we need to compute the partial derivative for this. So that means it's a denominator. So we should do square. And then apply the partial derivative of the. So what is the partial derivative of the? So a lot of algebra. But all you need is patience, actually, right? This kind of problem. You don't really need the real, difficult mathematics, just the patience. Then you do one by one, right? And so then scope function, right? Times density. dy. So that is actually is a expectation of a pi times scope function given x. So so that's why you get in the denominator you end up getting the same term, so that you get squares. So what we are doing is try to compute the information matrix to apply the scope function and scope. But luckily we got some cancellation. So we have a 1, 2, 3, 4 terms. Okay. So but it turns out that this guy and this guy cancels too. So first term and second term cancels to each other. Because why? Because if you take the expectation, right, of delta, then this guy and this guy essentially cancels. And then this guy, it becomes a pi times s dot. So pi times s dot. So then you cancel. So then end of the day, what you left with is the third term and fourth term. Okay.
So in your annotations, how did you get the last equality? So integral of
Here
from here to here. Yeah.
This one?
Yeah.
Okay. So yeah, I mean this is the several times. So we are taking the partial derivative of the density. That is the scope function of the density times density, right? So that is this one. Okay. So that basically take care of the cancels and so we take care of the 2 terms. So that is essentially this. So that is about computation. And now statistical properties. Well, remember it now it's relatively simple actually. We now. So what is SC? SC is a 1/n, I go to n, 1 to n, delta I, S theta xi, yi, minus conditional expectation. Given xi, delta equal to 1. Okay. So by just subtracting this, we make the whole thing as a zero expectation. So this is kind of essentially, you can see that SC is basically derived. So you can see that C is the score equation, score function derived from F1 y given x and zeta. Okay. So that is y given x and delta equal to 1, etc. Right? So suppose we just treat the this one as a density. Then this is just the MNE for this density. So that is and then you have information, right? Issue information corresponding to MNE. So that should be straightforward. Second property is more interesting. So now, if you think of all possible, all class of scaling function equations of this form with delta times u equal to 0. So one example of this, one of the example is, suppose this one. So this particular one is what? Propensity, right? So you just use propensity to solve zeta for zeta. And also another one is this one, SC, which is what you derived just now, right? From the conditional likelihood. So now question is, which one is better between the two? So the answer is, huh? Okay. The answer is, yeah, right. It's really good, right? Don't just follow the step. Always guess. You always guess first before you see anything. Before you go to seminar, you should guess what the speaker is talking about, right? Anytime, any conversation, you should guess. That's the very important to get intuition, right? Otherwise, if you just passively accept, you will never grow up. You may be good at understanding what professor is saying, but you cannot really do anything. So if you do anything beyond, you should give a try, no matter whether you are correct or not, right? So the answer is, this one actually achieves the lower bound. So that actually is very close to Cramer-Rao lower bound, right? You have the class of problem. So you have this is a kind of information matrix, information. So Cramer-Rao, this is the essentially very close to I don't know what there's some typo. Okay. So the proof essentially is very similar to to the proof of the Kramer-Rao row bound, showing the Kramer-Rao inequality. So here, I think rather than, so what is the, right? So the assumption is this. So rather than writing this way, you can write it so subscript 1 denotes the delta conditional distribution delta equal to 1. So, well, so this is actually something like u zeta x and y given x on delta equal to 1 dy equal to 0. So you have a, okay. Okay. So point is that you this is Bartlett, same as you need to first establish Bartlett identity. Says that you can show that u dot zeta is a covariance of u and S1. Let's assume p equal 1. Just to be, let's just make a life easy. What is the sorry? Let me. So remember. Did we? It should be negative, I guess. Did we get this kind of result before? I think we did it before, but we probably have forgotten. So for any, so point is that for any u zeta equal to xy equal to 0, whatever, then implies the function partial derivative of u hat, I mean, u is equal to minus covariance u and s. So why? Why? Because you can actually take the differentiation both side. Okay. Both side, and then you can do some sort of the partial differentiation here. Plus, if you do the expectation, see that's exactly equal to the expectation of the u and s. Right? I mean, here you have a dependence on zeta here and here, right? So this one is incorrect. The expectation differentiation is equal to expectation is an integration, right? Inside the integration differential of density. Density is the function, scope function times the density. So you get this one, right? And so that means this is 0. Okay, so this is 0. That means you get this one. Because scope function is, so this one is covariance. Okay, so that is good. And then which one?
Yeah,
This one?
yeah.
So you have a dependency here. So if you think of this one as an integration, you have an integration of u zeta and then f zeta, right? F x, y, and z. And then this one applies to f will reach in this system. Okay. So you get end of the day you get this. Now the solution. So let me see whether I can prove the solution to zeta hat to u equal, so u zeta hat u equals 0, right? You get this. Solution is basically you have a variance is a partial derivative of the round zeta, I guess, u dot. So expectation 1 over what is the tail? So if you do, let me okay, let's do one by one. So yeah, actually we have oh sorry. Okay. So zeta hat is a minus. If you use this kind of result, you essentially have a u dot inverse variance of u, right? So my point is that variance of zeta hat is a we talk about u dot square and variance of u. And then this one, the denominator is nothing but covariance of u and s and square and variance of u. So that you have a 1 over variance of s. Right? So that is kind of an argument in showing Kramer-Rao law bound. Or what the other way? Okay. Something like that, right? You have a right. You have this one. So then this is the MLE, right? And then all these you just use the U1. I mean, the distribution is actually subscript 1. Right. Okay. I don't have much time. Okay. So I have about 5 minutes. Now we want to use, so the conditional likelihood is very interesting idea, but the one limitation is that pi xy should be known, right? So this one requires pi xy is known. And another approach is that so should likely approach is that it's very interesting idea. So this is the simple setup. Suppose you are interested in y given x, and you don't have to know, or the only information is it depends only on y. suppose this one depends on only on y. You don't have to know the form. Okay. That means if this happens, then you are actually assuming that what? Delta is conditionally independent of y, actually x given y. Right? So that means you have something like this. So that means you can delta equal to 1. So how to create conditional likelihood for y given reverse distribution, y given x, you can, right? Because delta equal to 1, this is a valid conditional likelihood. And then from here, you use this property to derive. So this is the marginal distribution. And then, so this is a kind of an application of the conditional likelihood approach, where you reverse the relationship between y and x. So once you reverse it, then you can apply conditional likelihood, and then the reversed conditional distribution can be derived from the Bayes theorem. But you need a model for the marginal distribution of x. But you observe x, so you observe x throughout the sample. So you conceptually you should be able to compute. Okay, so then, so for example, you may just use empirical distribution. Then this integration is just sample summation empirical distribution. Okay. And this idea can be extended to more general setup where x2 is an instrumental variable. So that means x2 and delta is independent given x1 and y. Okay. So that is basically you need so once you have this one, you can basically construct the pseudo likelihood. And so that is the basically pseudo likelihood approach, and that that uses the responding unit, but you need some sort of the adjustment. Okay. And so this is developed by Jiwei Zhao and Jun Xiao quite a lot. So that is the basic brief overview of the conditional likelihood and its application. So, I'm sorry?
What is the advantage of this method, pseudo likelihood?
You don't need a model for pi.
Okay.
Okay. So that is the yeah, that's a good question. So otherwise you need a model, right, for pi, and which is hard to justify. You don't need because of missing data. You cannot really do some model diagnostics apply. So but this pseudo likelihood approach does not use the particular form of the propensity model, right? So that's
Instead, they are using the density for x.
but you do use this, but this is relatively easy to verify because you have a full observation index, right? Yeah, there are a lot of interesting ideas in missing data. How to catch up. Okay, that's all for any questions.
With
this one?
Yeah, so are we assuming
Yeah, this is a little bit tricky.
conditional and what is non-response instrument?
Huh?
So you said that is X is a non-response instrument. So, I mean, what is the instrument variable and what is non-response instrument?
That I covered in the beginning. So, yeah, okay. So non-response instrument means that it does not directly depends on delta, but it depends on Y. Okay.
Yeah.
So yeah.
Oh, okay.
Yeah, I think I covered too much in 1 day, 1 hour. So probably I can. It's not really your fault to digest. You cannot if you cannot digest all in 1 hour. So yeah, it's a lot actually. So I'm basically summarizing 10-year development of non-ignorable missing in 1 hour. So yeah, okay.